Good.
So it's our great pleasure to have João Ramos. João is an assistant professor at the University of Illinois at Urbana-Champaign and the director of the RoboDesign Lab. His research focuses on the design and control of dynamic humanoid robots, human-machine interfaces for whole-body teleoperation, legged locomotion analysis, and actuation systems. João, stage is yours. We are looking forward to your talk.
Awesome. Thank you so much for inviting me. This is great to be here. Thank you, Steve. Thank you, Majid. This is a great opportunity to talk about my work. So I'm João Ramos. I'm assistant professor at UIUC, and more recently, I started dual position as senior engineer at Boston Dynamics. So, but today I'll just focus on the UIUC stuff. So, today I'd like to talk a little bit about the work that I've been doing regarding design principles and performance metrics for dynamic humanoid robots. So I'm trying to quantify what we should be designing for, how we should be measuring their performance in order to make like a systematic framework for designing these robots. So starting at a high level, what I want to achieve is probably what everybody wants, every roboticist wants here. What I want to get to is robots that are really able to perform these dynamic motions at a human level. So is this choppy, by the way, or is it the video's okay?
It's perfect.
Okay, cool. Yeah, so what I want to do is get to this level of performance in which, the robot is really trying to exploit some dynamics and is trying to maneuver through an environment in a way that is very, very dynamic, such as like what we see in parkour and free running and things of this sort. The difference, though, is that I don't want to achieve this through complete autonomy on the robot side. What I'm trying to do is actually achieve this through human control. And I would argue that humans are extremely good at controlling things. So, for example, this is a video of a pilot piloting this drone through a very cluttered environment. And I would argue that, this performance rival or surpasses a lot of what autonomous drones can do. And, humans have this really good sense of anticipation and the maneuverability, and they can really build the motor skills. By the way, I love this part. It's really cool. So what I'm trying to do is actually achieve this kind of locomotion, parkour level of locomotion of robots through human control instead of doing through complete autonomy. The difference, though, is, if you're just trying to fly a drone around, or if you're trying to, maneuver your body throughout the environment in a terrestrial way, is a completely different thing, right? So when you're trying to jump around and run around, what you're trying to do is leverage your contact forces in the environment in order to translate your central mass. So you got to be able to, coordinate your whole body. You need to be able to combine, interact with the environment. You need to do these fast motions. You need to contact the world with multiple parts of your body. You need to be able to mitigate impacts. So pretty much what we need to do is have some robot that can have a human level adaptation to the environment. So I think we're probably very much missing a chance of leveraging, this human innate ability to control their bodies if we're not trying to use that to control humanoid robots as well, right? So the overarching goal of my lab, the RoboDesign Lab at UIUC, is to accomplish this. So the research in my lab is divided in three main topics. The first one is something I like to call controls over design. So it's how do you think about the design of these robots, knowing that they need to facilitate control in some sense, right? They need to be more efficient or faster or better inertia distribution or anything like that, right? So how do you think about design when you're targeting facilitation of controls? The second thing that we do is what I call human-centered control. So how do you control these robots when how do create control architectures for these robots when you know that you're going to be, in the end of the day, controlled by a person? So how should the robot follow the person's motion? How should the robot think about its own contact forces when it's trying to reproduce what the person is doing as well? And the third topic is kind of putting the two together. So how do you think about the human-robot interaction, right? So how should the robots follow the person is doing, but also provide to the person some sort of feedback that enables the operator to understand what is happening, and be able to replan their motion and do a better job. So I'll give a quick intro on some of the work that we've done on human-robot interaction, such that you I can give some context to what I'm going to talk about in design. But a lot of what I'm going to focus on today is on the controls aware design, which will be the second longer half of this time. Right? All right. So my work on what I called manipulation and telemanipulation and teleoperation began, some time ago in my PhD. And at the time we were doing just kind of like, I would say, crazy things. So for example, trying to get to put out this mock fire using a robot and doing some kind of what I call fine manipulations. And the thing that I would like to point out on this is that, these things are stuff that it was incredibly easy to do in teleoperation. We got it done the first day. And it's probably something that would take you a month of work in order to get the robot to do reliably. But also at the time, we're not looking to this kind of like fine, slow, dexterous manipulation of things. What we wanted to do is what we call forceful manipulation. So really, how do you teleoperate a robot to be able to create large forces, impact the environment, deal with this impact, and also provide to the person the correct force feedback in order for the person to control better the motion of the robot. And also, of course, if you build a motion capture system, if you build a humanoid robot, I don't see anything better to do than trying to punch things and break walls and stuff like that. So there you go. So, but this was the very beginning. At the time, honestly, we didn't know too much about what we were doing. We were just trying to explore what locomotion, what teleoperation would look like. So we went for manipulation. Next thing that I started looking at is what we call dynamic telelocomotion. And at the time, what I was trying to do is trying to figure out how can I capture the human motion and in real time convert that motion to a reference that is dynamically consistent to the robot to follow, and get the robot to follow that in real time. So this is probably one of my most important results from my postdoc and PhD. And I was able to get to this dynamically stepping place that was completely synchronous between the human and the robot. And here I want to do like a shout out to biomechanics, because a lot of my ideas here come from dynamic similarity. And I kind of like brought that to robotics, and it worked pretty well here. At the time I was trying to really explore what we could accomplish with teleoperation of locomotion. So I got to also try, this cute little jumps that we demonstrated here. And all this is accomplished by simply scaling the forces that the person is trying to produce. So for example, here the operator is on this force plate. And pretty much what I do is I capture that force that the person is applying. I tell the robot to apply a dynamically consistent force. And what it results that the robot takes off and jumps just like the person is doing. I think what is nice is that we could also leverage a lot of the results from autonomous robots as well. So for example, if we embed some autonomy on the robot can also start to deal with this, obstacles that's probably not present for the person. And in the end of the day, if the robot can still perform the motion, then the person don't need to feel any feedback of what's happening to the robot as well. So I won't get into all the details of all these things. I just want to talk at a high level what's happening. And for those of you interested, please check out our paper that came out a couple of years ago. So pretty much at a high level, what's happening is that, the first thing that we do is that we capture this human motion, right? So the motion is pretty much described by the motion of the feet, the ground direction forces, and the motion of central mass. And then we use some sort of reduced model that in this case is just the inverted pendulum to grab the most important components of that locomotion. We transfer that using dynamic similarity to the robot, so we can scale that motion to the robot. And then the autonomous controller just needs to figure out how does the forces applied on the ground reproduce that reduced order dynamics. So pretty much in the end of the day, what we want is that the two reduced models for the person and the robot, which in this case, the LIP, the linear inverted pendulum, are dynamically similar. Of course, there's a lot more details that goes into this, but this is the gist of it. So pretty much, if you can use this reduced model as a way to scale the motion, then you get the two to move synchronously. And more recently, you can probably see here that the robot in this case is constrained to the frontal plane. So there's a gantry there that holds it in place. So at the time, I was just doing frontal plane motion, but recently I was able to show, just get a motion out here, dynamically walking in simulation with my student just a few months ago. So what we're doing now is pretty much extending the idea of the frontal plane stepping in place to now dynamic walking, such that the person can control the robot to walk around. So pretty much, if you walk in place and then you lean forward, we can generate a spring using this haptic feedback device that we have here, and the person can just control the robot to walk forward. So you can control the robot's forward speed just by leaning back and forth. And what we're working on right now is on implementing this on the robot Telo that we've been developing in our lab. And in the end of the day, all we're trying to accomplish is dynamic telelocomotion on structured terrain by using human input. So this is the end goal. This is the dream. Hope to accomplish this in the next few years. But this is kind of the main research that we're doing in our lab. So what I would like to focus today more is on what I call controls-aware design. So in this particular case, I'll talk about some design principles and metrics that we developed specifically for dynamic humanoid robots. And in this case, the robot Telo that you see here, which is the mostly the work from my PhD student Young Sim. Okay. Okay. All right. So pretty much what I want to do is really depart from this old, paradigm of position control industrial robot manipulators. I would argue that, if you're trying to develop a robot that is actually supposed to interact with the environment, and touch the environment, and mitigate impacts and all these things, then you really need to rethink about how we control. From this old factory robots, what we wanted is to be, really high precision, really stiff, really high payloads, right? But if you think about it, this is not what we want from a robot that needs to interact with something that is unknown, right? What we want is a robot to be incredibly backdrivable, right? So if it's kind of like our arms, if you turn it off, you can kind of like move it around everywhere, and we need that transparency. You also want to have like a really high bandwidth for generating high forces. So if you step really fast to try to balance yourself, you need to be able to move your legs fast, you need to mitigate impacts fast, and you need to ramp up forces, contact forces fast. So your overall control bandwidth needs to be high. You also want to be able to mitigate impacts. So if you want to try to jump and you need to absorb that jump when you fall, you need to be able to do that compliant without destroying your gearboxes or any other mechanical component. But I would say that probably one of the most important ones is that you need to be able to produce reliable force control. It's not like, and I'm not saying about closed loop force control, I'm talking about real open loop force control. So if I command a force from my actuators, I want to get that force, and I want to get that force fast. So I would argue that we really need to rethink how we design these robots and how we think about the performance of these robots that is completely different from what we used to have. And I think a lot of people has started to go in that direction, but I would argue that we're not there yet. So a lot of the things that we see out there are empirical design principles for dynamic humanoids. So a lot of papers that you look at, you get sentences like this, maybe go like this one. Low gearing ratio will improve the backdrivability and force inertia and refract inertia, right? And in fact, if you look at the efficiency of gearboxes and compared to the gear ratio, the efficiency goes down exponentially, right? But the problem is that we don't have a good way to quantify what that is. How do we quantify backdrivability? Or maybe another one that we see a lot is, for example, we use actuators that have large radius because we want to increase the torque density. Okay, but how much is too much? Or how much should we go? What is the biggest actuator that can fit, right? How do you think about these things? And then one that I see a lot, and it was bothering me for the longest time, is then when you see something like, we place actuator near the body, so we reduce the moving inertia of the leg. Okay, but how much is good enough? Should I do very complicated mechanisms so I can put all the actuators near the body? Or could I tolerate some actuators to be more distal and then, hurt a little bit the inertia of the leg, but I'm getting into something else, right? So pretty much what I'm trying to do is, can we be more systematic about thinking about this robot and just instead of just empirically saying, oh, I want to achieve this, right? I want to be able to quantify, this is how much I get if I introduce this design, this is the trade-offs, and you can quantify what those design trade-offs are. So this is what I'm trying to do. These things are very clear, for example, for old manipulators maybe, and things of that sort. But there's nothing like this that exists for humanoid robots. There's no recipe or book that tells you how to design a humanoid robot. So what I want to do is go in that direction. So today I'll talk about 3 of these design principles. And the first one is something that I think is very important, which is backdrivability. So a lot of cases when you grab a electric motor and you try to move it, you grab the output and try to move the electric motor, we see that there's a relationship between the gearing ratio and how easy does it feel to move that. But we don't know exactly what that is like. We don't have a good way to quantify this at a robot level. So this, backdrivability, the way I see it, comes from a fundamental issue with the geometry of gearboxes. So for example, if you look at the geometry of a gearbox, I can condense that to a unidimensional problem. So in this case, forward driving, which means the motor drives the output, is equivalent to pushing with this blue force U and getting to move this big M blocks, which is a load. Backwards driving now, which is you grabbing the output and back driving the motor, is the other way around. So I apply, for example, a force X, and then I try to move the mass of the motor, which is a little m. The slope of this ramp here is equivalent to your mechanical advantage, right? So I won't go into the details, but pretty much if you write the equation of motion of this system, it looks something like this. So depending if you're moving forward or you're moving back, so if you're driving the output using the motor, or the output is driving the motor through the gearbox, you have a different equation of motion because your friction now changes direction, right? So if you compute the efficiency, that means that the forward efficiency is different from the backwards efficiency, which means that the power flow in the system is different. However, what I want to point out and what is the key thing that I'm trying to get here is that it is always the case that the forward efficiency is higher than the backwards efficiency. And there's a point in which, for example, 50% of forward efficiency of your transmission, in which you're completely non-backdrivable. So this is equivalent, for example, of if you have a robot manipulator and you try to move it and it's a complete statue, right? So it's zero backwards efficiency. And this is always the case. So the other thing that I want to point out is also that the efficiency of your transmission is also a factor of apparent mass. So pretty much that means that the worse is the efficiency of your transmission, heavier, higher the reflecting inertia of a manipulator, less backdrive it is, and worse it is to absorb the impacts. So what we're trying to do is actually quantify this at a robot level. So if you think about, the directional efficiency at a robot level, so for example, the entire leg of the robot, how does that go? So I won't go through all the details, but the high level idea here is that we start with the redundant system, in which considers the angle of the motors and the angle of the joints. And then we use the notion of directional efficiency in order to reduce to the minimal system. And pretty much in the end of the day, what we get is that we get a new inertia matrix, and you've got a new selection matrix that demodify both the reflecting inertia of the actuator and its capability of applying torque. I know this could have maybe just went through everybody's head, but what I want to get to in the end of the day is something that looks like this. So what I want to be able to is, a priori, before I build my humanoid, I want to be able to compute if a joint being backdrivable or not is something that's going to affect the robot's performance or not. And then this is what we get to do with this modeling that we're trying to perform. So pretty much just for you to have an idea, this is the computation of the reflected inertia, depending on what kind of friction model you assume. So for example, if the robot is completely frictionless, then you get the blue ellipsoid. So that means that's how much inertia you feel if you move the foot around. Now, if you have imperfect gearboxes, which means that the gearbox maybe has 80% efficiency, that inertia is going to feel larger, right? So at some point, the inertia is going to be so big that it's as if the foot has infinite inertia. So what I want to do is be able to quantify how much that is. And the other way around also works, right? So, if the robot has imperfect transmissions, it also affects the ability to produce force. So if you have your force capability to polytope, that is going to be, shifted around depending on the transmission efficiency. So this is our effort in trying to quantify what backdrivability means in a way that it can possibly design things a priori. The second thing that I wanted to talk about is what we call centroidal inertia isotropy. And this idea came from a really iconic paper from Goswami that talks about inertia shape. So pretty much the key idea means that if depending on the pose of the robot, the whole inertia of the robot is going to vary, right? So maybe if the robot is standing like this, the centroidal inertia looks like that. Or if I'm doing something like this, it will look like more like a sphere. My point is that if you imagine that your limbs are massless, completely massless, it doesn't matter how you pose them in space, the inertia will always be the same, right? So this is a way that we thought about to quantify how close to the body should be placing actuators, right? If you place your actuators very far on your body and you're trying to pose everywhere, your inertia shape is going to vary a bunch. But if your actuators are very close to the body and you move everywhere, your inertia will not vary too much. So the CII is a way to quantify the distribution of inertia depending on how you pose your body. So it's pretty much given by the ratio between occurring inertia and some nominal inertia, maybe the robot just standing around. And then you get a distribution that is dependent on configuration. So for different poses of the body, you get a different value of the CII. And what we want maybe is the CII to be completely flat. I want to be the same everywhere on my configuration space. So what we did is that we quantified this for a bunch of robots. So for example, Mini Cheetah, Telo, which is our robot, Cassie, DSC Atlas, and Hubo. And what we get is a bunch of these curves that is a multidimensional curve that depends on the configuration of the robot. So for example, you see that, for example, Cassie is a lot better than Hubo. Hubo, it doesn't, whatever position it poses itself, it completely varies its inertia. But Cassie has a much more flat inertia distribution, which is something we always try to design for. And something that we try to quantify is if you take the maximum inertia and the smallest inertia, and you take that difference, what happens is that varies dramatically depending on how dynamic your robot is. So, quadrupedal robots that have very massless legs, there's no way to compete with them, have very good difference. So this number is very small. For humanoid robots with proximal actuation, which means actuators are close to the body, their number are modest here, right? So that's Telo robot or a Cassie, the ones that we're designing for. And then robots that have co-located actuation, which means motors at the joints, have a very, very bad inertia distribution. So that means that, when they move around, they're swinging a lot of mass around, which is something that you don't want. So in the end of the day, what we want to do is compute the distribution of inertia such that we can get a number of, how good or how bad it is for a given design of the robot. And what we saw is that usually robots that tend to be more dynamic have a better inertia distribution. So it's something that we, backwards checked afterwards. All right, and the last principle that I want to talk about really quick is what I call cooperative actuation. So pretty much what we're trying to design for is sometimes when joints are not used at the same time, sometimes it's a good idea to combine some of the actuators. So for example, Telo is a robot that has a differential linkage on the hip and also has a differential that drives the knee and the ankle. So I won't get too much into the details, but it pretty much means that if you have a trajectory in blue, which is your joint requirement trajectories, right, for a test, let's say running, you're going to have like a torque trajectory and also a velocity trajectory, these two. What we can do is grab your motor capabilities, which is this gray square, and you can use a gearbox to, amplify the torque capabilities of your motor and try to fit it. But what happens is that if you also try to combine motors, saying, for example, a differential configuration, what happens is that you can move that, amplify that square and also move it around. So in the end of the day, what we want is trying to minimally inflate the motor's torque and speed capability to try to encompass the trajectories that we're trying to achieve. Because every time that we inflate the motor, that means we're adding more gearing. That means we're increasing reflective inertia. So depending on how we combine motors, and in this case, for example, differential configurations, you get, better torque capabilities, but without inflating the reflective inertia too much. So this was a cute little jump that we did with a humanoid robot. And what we're trying to show is, for example, for this jump that mostly requires knee torque and very little ankle torque. In fact, there's no ankle here if you look. For example, we produce 20 Newton meters at a joint level, but only require 10 Newton meter at motor level and only 30% more speed. So what I want to say is that if you have motions that require a lot of a single joint, but not a lot of another joint, maybe it's a good idea to combine the actuator for those two joints, right? Okay, so there's a lot more design principles, but the ones that I wanted to cover today, maybe the most important ones is, what I want to do is maximize the efficiency of your transmission. That improves backdrivability, your torque control capability, and improves your reflective inertia. You want to also maximize your CII, your inertial distribution. That reduces your limb inertia and also makes your centroidal inertia more constant, which is very good for controls. And the third one is you want to employ cooperative actuation. Maybe you want to combine motors with some joints because that will allow you to have more force capability without inflating too much your reflective inertia. And then if you can make all these things work together, then you can probably get to robots that are acting more dynamically. All right, so the last thing that I want to just mention really quick, I'm very glad that I'm leading a team, a multi-university team that has just been awarded 1.2 million from NSF. And what we're trying to do is design an open source dynamic humanoid robot called Dash. That's going to be super cool. So what we're trying to do is design for a robot that has capabilities that go from sprint running and powerlifting and loaded carry. What we're trying to do is design a holistic framework that think about the design of the robot and controls at the same time. So the project just started last month, so we don't have a lot to show yet. But here's a web page. Please keep tuned. But I'm very excited about this initiative, and I think it's going to be great, and I hope a lot of people will get to build their own dashes. So with that, I want to finish, and I want to take any questions if there's any. Thank you so much.
Thank you so much, João. Also, we are very much looking forward to your new robot. So if there is any question, either please again write in the chat or raise your hand. And yeah, is there any question? Side? Yeah.
Thanks a lot for the interesting talk. So I actually have a few questions. Yeah, sure. So my name is Guoping, and I'm a postdoc doing the biomechanics in Locomotion, and what I'm focused more like in bipedal locomotion and also axial control. So the first question is related to the teleoperation. So it's quite interesting to see that by only applying or having some sort of bidirectional feedback in the foot placement and also the trunk between the robot and the human, you can achieve such good results. And I'm just wondering, would it be better or worse if you also introduce bidirectional communication between like different links or joints? It will be similar like axle. So if you have a lower limb axle, then basically you will have more interactions.
Yeah, so this is a great question and something that maybe I've been thinking about for a long time. And the whole point is that, locomotion, let me just get to the video that I showed. Okay, there you go. So the whole thing about locomotion and eventually mobile locomotion in manipulation is the fact that it requires coordination of the entire body, right? I need to coordinate where I'm placing my feet, what kind of forces I'm generating, what my arms are doing. And in the end of the day, the amount of feedback you give to a person can, be too much. It's just too many things to pay attention at the same time. So what we're trying to do here is actually try to reduce that. So instead of, for example, giving force feedback to their hands and their feet and their body, what I'm trying to do is provide a single force feedback to their central mass, which is kind of the net wrench of all the forces applied to the robot. So I'm trying to give to the person a condensed information of all the forces applied to the robot. And what I'm trying to do is kind of like reduce the cognitive load associated with driving the robot. And a lot of these has to do with how autonomous robots are controlled, right? In the end of the day, what we think about is our wrenches applied to the central mass of the robot. So what I'm trying to do is leverage that idea and use that as a feedback as well. I would like to add feedback to hands and feet. The issue becomes that the amount of feedback that we want to give is something on the order of like 150 newtons, 200 newtons. And then if you try to build a device that can do that, usually their reflective inertia is very high. So in the end of the day, it's just a lot of effort for the person to be moving so many things around. So what I try to do is condense that into a single force information, which is in this case, for example, these two rods here applied to the person's back. Did I answer your question?
Okay, great, thanks. And the second question would be more related to the backdrivability for your calculations. So I think, does it actually only apply for the gearbox, like the plenary gearbox, or it kind of like general purpose? Because I thought it might be different if you have like a belt reduction system or some other transition system, right?
Yeah. Yep. So it's highly dependent on the transmission. In this case, I'm just showing for spur gears on, for example, spur gear or planetary reductions. However, it is almost, I don't want to say always, but it's kind of like almost always the case that whatever transmission that you use has directional efficiency. So if you drive one way or drive the other way, is a different efficiency. For example, belts, those is almost the same. But for example, harmonic drives, they're very different. And the proof of that is if you try to back drive a harmonic drive, it feels incredibly difficult, right? It's kind of like, so that means that the backwards efficiency is very small. It's very low. The model to calculate that efficiency will be different from what I'm showing here, but it's almost always the case that they are different. So as long as you can quantify this, the forward and the backwards efficiency, this is what we want from the model. You can even measure that experimentally if you don't have a model for it.
Yeah, right. And third question related to the, thanks. And third question is related to the lag property or lag inertia. So at the beginning, you showed a video of the parkour of humans doing like jumping and flipping. And for humans, the lag mass inertia is like 15 to 20% of whole body. While like here, in your conclusions, basically, if you have as less as possible, the lag mass or lag inertia might be you have a like really most agile dynamic locomotion, but actually it's not the case for human at least, right?
Yes.
So do you have a comment on that?
It is always like a design metric, right? So for example, if you want to stand and I push you, you kind of do this with your body, right? So if your arms are massless, you cannot react to disturbance like this. So having massive limbs sometimes is beneficial, right? Some animals use like tails as reaction masses. However, what I'm saying is that this is a way that you can quantify that. So in a lot of controllers for humanoid robots, the controller thinks of the robot as a centroidal dynamics or a single rigid body, right? In that case, it is beneficial to have a very flat inertial distribution. But if you're trying to use a robot that kind of trying to leverage its body to make a task, in that case, you do want to have like a non-even inertial distribution. So what I'm trying to provide here is a tool to quantify this. I'm not saying that it's always I'm not going to say there's always a case they want it flat, but here's a tool that you quantify how flat it is, and if that fits what you're trying to do with your robot.
Great, thanks a lot.
Thanks for your questions. It was great.
We have another question here. Give me one. Oh. Great. So thank you for your talk. I just have, my name is Rohan. I'm a PhD student at JRL it's in Japan. So I know your presentation was more about what's the best design for making a new humanoid robot for more compliant force torque control. But do you have any comments on how can we make existing robots that were initially designed for precise position control and that have a higher gear ratio and that are less backdrivable. Do you have any comments on how can we make them better for like torque control? Because I know there's some works that try to do adaptive friction compensation. So do you have any hope?
Yeah, so I think there's a tricky question. And I think it's because the actuator is fundamentally built for a different thing, right? So for example, you can do a friction compensation, but the problem is that friction compensation, if you try to move something at very high frequency, friction compensation could become positive feedback, right? Which could turn into instability. So what happens is that, and so if I grab a hammer and I hit the robot and the robot is position control, the robot does not have sufficient bandwidth to get out of the way fast enough, right? So what happens is that the robot fundamentally cannot behave at the frequency that we're trying to operate on dynamic motion. Something that I think is a good idea is that if you're stuck with position control and you want to do force control, then adding a series spring could be beneficial. But the problem is also the thing that, you know, if you have a very soft spring, that limits the bandwidth of how fast you can build up forces. And then if you have a very stiff spring, that is, you know, going back to your old position control thing. So I think there's an inherent problem there as well. So I think that if you cannot get rid of position control at all, maybe you want to prioritize some joints, right? So maybe, for example, if your robot is running, maybe just replace the knee actuator for a backdrivable one, and maybe that's okay, right? Or maybe just add a series of spring to the knee. But you need to be able to passively absorb impacts and deal with contact, just because it doesn't matter how fast your controller is, you're never going to be faster than shock waves, right? These are fundamental things. So maybe you want to try to think about prioritizing some joints, or maybe you want to try to think about adding like a very thick pad to the robot's foot. So now you can, you know, slow down those impacts or maybe control force at that level. But I think you're introducing dynamics to something that has already very complicated dynamics. So you're just making your life harder.
Yeah. Okay.
Sorry if I didn't solve your problem, but this is what I think.
I have a question for your teleoperation. So you mentioned that actually, I think in answer to Guoping's question, that you try to use a very minimal set of quantities for feedback to the user. What about in the other direction? I imagine the user can actually sort of like command things that the robot might not be able to actually track. Is there a single quantity that you can sort of monitor to see, oh, you're not going to be able to do this safely, don't even try tracking it?
Yeah, so pretty much the philosophy of what I'm trying to do here is that the robot's performance is only going to be as good as the reduced model that you're trying to use, right? So if you're trying to use, if you just have an LIP, but you're trying to get the robot to run, it would probably not be a very good idea, right? So you need to build a model that is able to capture the dynamics of what you're trying to do with the robot. So in that sense, I think that the same notions that we have from autonomous robots apply here. If we have a certain model and you have a robot with certain dynamics, can the model produce the motion that we try to do with that robot? Yes, then I should be able to teleoperate using what I'm showing. No, then the teleoperation here will not work. So it is a hard answer just because I don't know how to quantify stability in locomotion and like locomotion. But it's pretty much if your reduced model can do it, then this teleoperation should be able to demonstrate that.